Yeah, welcome everybody to our third Spatial ML seminar. So today we have Petros Toupas. Petros received his MEng from the Electrical Computer Engineering Department of the Technical University of Crete in 2018. And since then, he has been working as a research assistant and a software engineer um, at the Information Technologies Institute, the ITI, of the Center of Research and Technology Hellas, which is CERT for short. And in 2020, he started, in collaboration with Sturs, his PhD at Imperial College London, where he's currently studying. And his primary focus is, as you will see in this talk, is in the area of machine learning acceleration, computer vision, video processing, and how do you do all those things efficiently on reconfigurable architectures and FPGAs. Petros, thanks for making the time to give this seminar, and the floor is yours.
Thank you very much, Andrew, for the introduction, and thank you for the opportunity. Hello, everyone. My name is Petros Toupas from Imperial College London and CERT. And today I'm going to present you our work named HARFLOW3D, a latency-oriented 3D-CNN accelerator Toolflow for human action recognition on FPGA devices. Let me firstly introduce you to the human action recognition and give you an insight about what it is and its applications. Human action recognition is the task of identifying or classifying human actions given an input video clip of a fixed duration, assuming a single action is being performed per clip. It finds use in many applications like entertainment, healthcare, activities of daily living, and video surveillance. But how is human action recognition used in practice? Given an input video clip of m frames in total, we need to sample k frames out of it based on a sampling rate R. This will provide the input volume that the DNN expects to perform the classification task. The current state-of-art solutions are mostly deep learning based and dominated by either transformers or 3D-CNN architectures. Looking at the graph, one can tell that 3D-CNN architectures require orders of magnitude less parameters, meaning reduced memory requirements. So when it comes to deploying human action recognition models on the edge, 3D-CNN seems the best candidate. The requirements and limitations of the edge devices and the rapid evolution of such architectures in the field make the FPGAs a suitable candidate as a target platform. But how does the complexity and memory needs differ between the 3D-CNNs and 2D-CNNs? In the figure on the right, we can see both 2D and 3D convolution execution flow. In the 2D version, a kernel shifts across the X and Y axis of the feature map, providing the output pixel value for the respective part of the input. In the 3D case, the kernel is expanded to account for the extra temporal dimension. The same thing applies to the input and output feature maps. The kernel now shifts across X and Y axis, but also shifts on the Z axis, accounting for the depth of the volume as well. As it is apparent, the storage, the computation complexity, and the bandwidth requirements are much higher in the 3D case, leading to much wider range of design choices, and hence making the optimization and mapping of such models a challenging and non-trivial task. This cannot be handled by the existing solutions on the 2D-CNNs, so we propose this work. To further elaborate on the 2D versus 3D-CNN complexity and memory needs, the table in the bottom showcases how resonant statistics like multiply and accumulates, like feature maps, memories, and parameters escalate moving from 2D to the 3D version of it. The current FPGA solutions on 3D-CNN support rather old 3D-CNN models like C3D and are mostly hand-tuned hardware designs that are tailored to the characteristics of the specific model. There is also a lack of a tool flow for an end-to-end mapping of multiple and more recent 3D-CNN architectures to various FPGA platforms. We aim to fill this gap by providing such a tool flow depicted at the bottom of the slide, addressing all of the above points. Our tool accepts a DNN model in ONNX format as well as an FPGA platform specification. After that, the model is parsed by the internal parser and converted to an intermediate graph representation. After that, the DSC, the design space exploration, starts by altering and optimizing this graph in order to find the best possible design point. Once the optimization is finished, the hardware mapping is executed in order to generate the bitstream of the final design. So, our contribution. We introduce and propose HARFLOW3D, the first 3D-CNN tool flow in the field. The key aspect of the tool flow is the introduction of a highly runtime parameterizable hardware blocks that allows us to provide low latency designs, which are positioned on the Pareto front of latency against accuracy on a UCF 101 benchmark. This is a widely used benchmark for human action recognition models. At the same time, the tool flow provides support for the state-of-the-art 3D-CNNs that has not been previously addressed by the FPGA community. So let me introduce you some of the core components of our proposed hardware design. First of all, a set of hardware blocks supporting the operations of the 3D-CNN models, like convolutions, pooling, activations, element-wise, and fully connected layers. These blocks come with a so-called baseline parameterization support, which includes tiling of input and output feature maps, a folding factor exploiting the parallelism over the channels and filters, namely coarse grain folding, a folding factor exploiting the parallelism in the dot product of convolution and fully connected layers, namely fine grain folding. The next core hardware component is a crossbar, which is responsible for routing data to the off-chip memory as well as for inter-hardware block routing. And of course, the DMAs, which are passing the data to and from the off-chip memory. But how do we use and combine all these hardware components towards the complete hardware design? We defined a baseline design where a single hardware block is introduced per layer of the 3D-CNN model, and each hardware block supports the parameterization that we have described in the previous slide. So tiling, coarse, and fine factors. Towards progressing, towards progressing to the first optimization step, we have introduced the fusion or merging of the hardware blocks, which means designing more generic hardware blocks that can map and execute the workload of more than one layer of the 3D-CNN model in a time-shared manner. However, this leads to some redundant calculation that must be performed due to the need for padding in order to correctly execute the support and support the variable feature map sizes among different layers of the model. But this is something that we are going to deal with later on. The next optimization that we have introduced allowed us to support sequential execution of any layer followed by an activation layer without needing to send the data to the off-chip memory through the DMAs. This is accomplished by adding the shown crossbar, which are able to map the output of a non-activation layer into the input of an activation layer. The final and the most important optimization is the runtime parameterization of the hardware blocks. It is important to mention here that the architecture of the hardware blocks follow the streaming architecture paradigm. Hence, the buffering plays a crucial role in the performance of these blocks. So, runtime parameterization signals are being sent from the host code on runtime and are responsible for changing the depth of the buffering needed for the input feature maps, like the line buffers, as well as the accumulation buffers for the accumulation of the channels in the output, which significantly reduces the padded calculation needed, as previously described, and greatly increases the performance of the hardware blocks. This has led to 18x improvement compared to the baseline design. So having established the main hardware architecture, here we provide an example of how the data flows through the processing through the proposed design. On the left, we see the high-level architecture of a tiny model, an example model, and its respective layers. And on the right, we see the hardware level design with all the necessary hardware components. So starting with the first tile, we pass it through the DMA to the convolutional layer, which utilizes the crossbar to send the data to the activation layer. So at this point, we don't need to go to the off-chip through the DMA out. After the activation is done, is completed, we send the data to the through the DMA to the DRAM to be processed by the next part of the model. This continues for the rest of the tiles until we have the intermediate feature map complete, and we can execute the next layer in our model. All of the parameterization of the hardware blocks, like tiling shapes, coarse fine factors, as well as the hardware blocks fusion and merging, are being searched for the optimal values during the design space exploration. In each step, the optimizer and scheduler cooperate to provide design points, altering all of the aforementioned parameters. The resource and performance models are responsible for ensuring the validity of the proposed design, accounting for the constraints given at the start of the optimization procedure. The error rates of performance and resource model estimates compared to the actual board and Vivado measurements are the following. For latency, we've got a mean average percentage error of 6.64%. For DSPs and VRAMs, we have a 0% error. For LUTs, a 7.10%, and for flip-flops, and minus 9.4%. More detailed information on the optimization and scheduling algorithms are also can also be found in the paper, as well as the resource and performance models. So the evolution of the design space exploration over time is shown on the graph on the right for R2+1D on a VC709 board. The graph shows the Pareto front involvement on DSPs against latency. It is apparent that the optimizer is able to traverse the resource performance design space, providing a fine-grained control over this trade-off. The optimization task takes approximately 10 minutes to execute, but this also varies depending on the model complexity and the FPGA target platform. So the ability of HARFLOW3D to support and target multiple FPGA platforms allows us to directly compare our results to the rest of the works under mostly the same setup. CD3NN model was chosen due to the fact that most of the existing works have provided the results on this specific model. As we can see, HARFLOW3D is able to either surpass or provide competitive performance compared to the existing works, despite the fact that it's a generic Toolflow and not a hand-tuned design like the rest of the works. The presented table shows the variety of the models supported by each of the existing works in the field. As previously stated, most of the existing works have given their focus only on few 3D-CNN models and mostly on C3D. Opposed to that, HARFLOW3D is able to support and provide solutions on a much wider variety of more recent and state-of-the-art 3D-CNN models. The supported models and their respective hardware designs emerged from HARFLOW3D not only achieve competitive performance in terms of latency, but also have higher performance in terms of accuracy, which places them in the Pareto front as previously shown. So to conclude, we have introduced HARFLOW3D, which is the first 3D-CNN Toolflow that is able to map various state-of-the-art 3D-CNN models and targeting multiple FPGA platforms. The designs produced push the Pareto front, and the main and the core component of our design is the highly parameterizable hardware blocks. Thank you for listening, and I'm open to any questions that you may have.